So let me go through some announcements. So today there was the first lab. I did mark you in, Mariana. So today was the first lab. So your first homework assignment, getting started with WebAssign Astronomy, is due on Friday the 6th. You need to access that through Blackboard. So if you go to Blackboard, go to the homework section. The first time you sign in, you need to go to this link to sign in. If you have an account already at Cengage, you can sign in with that. If you don't, you can make a new account. You want to go to individual assignment links, they're in this folder. And you can go to anyone directly. The first actual homework assignment, so the getting started with WebAssign is a very easy and straightforward assignment. You're just, it's just about how to use the software. So, it has questions like, mark the answer that is labeled as the correct answer. Your very actual assignment on chapter 1 is the first chapter 1 is due on Monday, the 9th. And the second chapter 1 assignment is due on Wednesday, the 11th. Those are both on WebAssign. Your significant figures worksheet is due on Monday, the 9th in class. You can turn it in then. If you finished it already and want to turn it in early, I'll take it. If you need a copy because you didn't get one from David, I have a few extra copies up here. Yes. Yes, that was the last thing I was going to get to. If you missed your appointment or haven't signed up for an appointment, you can sign up for an appointment up here on this sign up sheet. But we'll do it after class. If you're finished, yeah. Turn it in right here. Thank you. So we will have our first quiz on chapter 1 on Monday next week in the SI session at noon in room 332. That'll be the first quiz. So, anything else? Don't think there's much else. We're going to be finishing chapter 1 today. We'll have the quiz on chapter 1 in the SI session. Any questions? It'll be in the SI session that starts at noon in room 332. What? You get to. So what do you mean? What were you? You can put whatever you want on it. So we're not. I mean, that would be the stuff you already covered in SI, or we're not doing a specific review before the quiz. We do a specific review before tests, but those are also in the SI session. So, but you can go through your notes and put what you think you need on it. So for example, if you don't think you can remember what all the metric prefixes mean, you can put those in your paper. So to continue on with what we've been covering. So yeah, you take the quizzes in the SI and I'll try and grade them as soon as possible afterwards. We were talking about scientific notation. So scientific notation, in scientific notation, a number is expressed as the product of two numbers, some number between 1 and 10, and a power of 10. And to convert a given number to scientific notation, what you do is you move the decimal point so it is immediately after the first non-zero digit. So the number ends up between 1 and 10. And when you move the decimal point to the left, you have to increase the power of 10 by 1. When you move the decimal point to the right, you have to decrease it by 1. And if there's no power of 10, that is 10 to the 0. So for example, here, 950,000, we have to move the decimal place 5 places to the left. So we have to go up by 5. So we get 9.5 times 10 to the 5th. That's a quick summary of the metric of that. We also talked about the metric system. The metric system uses the acronym MKS system from our standard units of length, mass, and time, the meter, kilogram, and second. This is to compare it to an older system that was also metric, but used the centimeter, gram, and second, called the CGS system. It's a decimal base 10 system. This is much more convenient than the US customary units or the British system, which are several different systems mixed together so that units are not, how you go from one unit to another is never consistent. And it's how you go from from a smaller unit to a bigger unit, or from a bigger unit to a smaller unit in the metric system, is always by multiplying by a power of 10, which means just moving the decimal point. It's administered by the International Bureau of Weights and Measures, the Bureau International des Poids et Mesures, BIPM in Paris. It's the International System of Units, which is abbreviated as SI, because in French it's System International. And there are 7 base units. The 7 base units are the meter for length, the kilogram for mass, the second for time. Everything involving motion, force, energy, things like that can be done with these 3. We will also talk about a little bit of some of the other ones later, specifically Kelvin for temperature. The ampere is for electrical current. The Kelvin is a measure of temperature. Kelvin is like degrees Celsius, except measured from absolute 0 instead of from the freezing point of water. It's the same size as degrees Celsius, but it starts at absolute 0, the coldest you can get. The mole, which is an amount of a substance, it's like a dozen, but a much bigger number. It lets you count molecules by weighing. And then the candela, which is a measure of luminous intensity. How bright something is. And the metric system lets you go from the base unit to various larger or smaller units by using prefixes. And each prefix corresponds to a power of 10. So if you have no prefix, that's 10 to the 0, or just 1, it's just the unit. So just say a meter. A meter, if you have M for meters, it's just a meter. But going smaller, you could have decimeters. A decimeter is this long. It's a 1/10 of a meter. Then you have centimeters. Centimeter is this long on a meter stick. It's 1/100 of a meter, 10 to the minus 2. Then you have milli. Milli is 1,000th of a meter. That's one of the individual lines on this meter stick, or on the ruler you use in lab today. Then we have micro, that's a millionth, or 10 to the minus 6. That is written with the Greek letter mu, which looks like a U with a line on the front. Then we have nano, which is 10 to the minus 9. That's a billionth, written with lowercase n. So deci is a lowercase d, centi is a lowercase c, milli is a lowercase m, nano is a lowercase, micro is a lowercase mu, nano is a lowercase n, and then there's pico, which is 10 to the minus 12. That is a trillion. That's a lowercase p. There's actually a step beyond, which is femto, but we won't need that in this course. And then going up, we have kilo, which is a lowercase k. That's 1,000. There is actually a 10 and 100, but they don't get used very often, so you don't need to know them. I think the 100 is a hecta. I can't even remember the 10. Then there's mega. That's 1,000,000. That is an uppercase M. So it's important to differentiate between uppercase M and lowercase m, because those are different units. And there is at least one problem on your homework where you need to make that differentiation. And then there's giga. That is 1,000,000,000, uppercase G. And if you use computers, you're probably used to those as they continue. Giga, the next one is tera, the one after that is penta. So, you know, if you have a terabyte hard drive, that's got a trillion bytes of data on it. And you have a petabyte hard drive, it's got 1,000 trillion. So, yeah, 10 to the 50. Yeah. Just quickly check that I'm in the right. Yes. So, significant figures. Significant figures are a method of expressing the precision of measurements and it's something that you have to preserve from when you do calculations. So, in a mathematical operation, such as multiplication, division, addition, or subtraction, it generally can't give you more significant figures than you start with. Specifically, multiplication and division, you are supposed to preserve the number of significant figures. Addition and subtraction, you should preserve the number of decimal places. That's the formal rules. But on tests and quizzes, if you just use significant figures, it'll always be okay. I'll accept both. So here, for example, 6.8 has 2 significant figures. 1.67 has 3. So if you do 6.8 times 1.67, you'll get 11.356 on your calculator, because your calculator will just give you the answer to as much precision as it can. It assumes the values you type into it are exact numbers, and it calculates as best it can the exact answer. So when you record this, you then have to round that answer to 11. To only have 2 significant figures, because you have to round to the lowest number of significant figures you have from your inputs. So as an example, when you use calculators, you do 6.8 divided by 1.67. Division leads to lots of additional figures usually, because not everything creates a nice terminating number when you divide. So 6.8 divided by 1.67 gives you something like 4.071853. For this, you would have, again, 6.8 has the lowest number of input significant figures. So you would round to 2 significant figures and get 4.1. So the general rule, only record as many significant figures in the result as there are in the input quantity with the least. So 6.8 centimeters divided by 1.67 centimeters would be 4.1. 6.8 is the limiting term with only 2 significant figures. 5.687 plus 11.11 will equal 16.797. We round this to 16.8. Here, the limiting term is 11.11 with 4 significant figures. These both have 4 significant figures. Strictly speaking, this should be rounded to 2 decimal places. But you'll notice that that works the same as rounding to 4 significant figures. That's fairly common. And I'm never going to be super picky about it in this class. But strictly speaking, for addition and subtraction, you should round to the right number of decimal places. And then for multiplication and division, that's when you take into account significant figures. But if you just use significant figures and round at the end, that'll generally be fine. So, some rules about significant figures. All non-zero digits in a number are significant. So 23.4 and 234 both have 3 significant figures. Zeros are significant if they're between any non-zero digits. So in general, the way you count significant figures, you start at the beginning and count. So here we have 20, 1, 2, 3, 4. These are in between non-zero digits, so they always count. So 20.05, that has 4 significant figures. 407, 1, 2, 3 significant figures. Zeros on the front, leading zeros, never significant. So here, 0.00035 only has 2 significant figures. These zeros just serve to tell you how big or small the number is. They don't tell you how precise your measurement was. So these are never significant. So in general, the way you start counting significant figures, you start with the first non-zero digit, and then you count digits to either the end or the last non-zero digit, depending on whether or not there is a decimal point. So digits at the end, zeros at the end, trailing zeros, if there is a decimal point, they always count. But if there's no decimal point, they generally don't count. So 45.0 has a decimal point. So we count the trailing zeros. Well, 4500 does not. So there's only 2 significant figures here. So 45.0 has 3 significant figures. 4500 has 0. If I wanted to write 4500 with, say, 4 significant figures, I would write it like this, 4500, and then I'd put a decimal point at the end. I will often do that on tests and quizzes, so I can give you a nice round number, but I want you to use more significant figures. So look for numbers with a decimal point on the end like that. And so trailing zeros are always significant if there is a decimal point, and they're generally not significant if there is no decimal point. And if you wanted to represent 4500 with 3 significant figures, there's not a nice way to do it in standard form. But if you write it in scientific notation, which would be 4.50 times 10 to the 3, in scientific notation, all the digits in this part are significant. And this is, you don't count this at all. So this would have 3 significant figures. So in the mantissa, I believe that is called. Additionally, if you have an exact number of things, like say you have 20 pennies, that would be an exact number. You would not, that would be assumed to have an unlimited number of significant figures. And so all that means, if you have an exact count of something like that, you don't have to worry about the number of significant figures from it. You can just ignore it and only look at the other things. So the general rule, we look at the input that has the least number of significant figures and round to that many significant figures. And in determining the allowed number of significant figures, we generally have to round off numbers. So the rules for rounding are generally, so for significant figures, you count from the first non-zero digit. So here, 1, 2, 3 significant figures. You want to round to 3 significant figures. Then we look at the next digit. This is a 4. If the digit after is from 0 to 4, then this is closer to 26.1 than the next number up, which would be 26.2, because this is less than halfway to 26.2. So we round down, we get 26.1. However, here, we again have 3 significant figures, 1, 2, 3. We look at the next number. That's a 6. This value is closer to 10.1 than it is to 10.0. It's closer to the next number up because it's more than halfway to the next number up. So we'll round this one up to 10.1. So generally what you're doing when you're rounding is you're looking at the number at the 2 numbers on either side of the number that you're interested in. So if you had, you'd have 26.2 and 26.1. Your number is somewhere in between those values. So this one was what, 4? So around here, this is 26.4142. And you're just choosing which of these it's closest to. And the rule for that is that if it's less than 5, if the next digit is less than 5, it's closer to the lower value. If the next digit is 5 or greater, it's closer to the higher value. Any questions about that? So here are some examples. This is a weird special case. We're rounding off 0.0997 to 2 significant figures. So if we start with 0.0997, we count 2 significant figures, 1, 2, we draw our line. Well, this is a 7, we have to round up. So if we do that, we get 0.100. But that has 3 significant figures. So all we do is we drop that last 0. That weird case where you get an extra significant figure that you have to drop will only happen if you have a string of 9s like this. So in practice, it basically never happens. Here we have 5.0 times 365. You do that on your calculator, the exact value is 1780. If we round 1780 to 2 significant figures. Oh, I misspoke. It's 5.0 times 356, not 365. I switched the numbers around. We round 1780 to 2 significant figures because 5.0 only has 2 significant figures. That would round up to 1800. So when you're making measurements, generally what you can do is when you make a measurement, on our last lab, I didn't actually make you do this extra level of estimation, but the general rule for measurements is you measure to the level that you can get from the device, and then you estimate an extra digit for the space in between, for something like a ruler. Or on a scale, however, you just read off what the scale says. So here, you wouldn't say the error was at 54 or at 55 or even at 54.6667. You estimate 1 digit and more isn't allowed. So you're going to involve quantities in a measurement, and these calculations depend on the accuracy of the measurement or the precision of the measurement, which you'll record with significant figures. So here, you would estimate this as 54.5 millimeters, assuming this was a millimeter ruler. So this measurement got 3 significant figures. So the rules for significant figures. In numbers with a decimal point, leading zeros are never significant. This is always true. Trailing zeros are always significant. That is only true if there is a decimal point. So if there's a decimal point, trailing zeros are significant. And zeros between non-zero numbers are always significant. That is, again, always true. Without a decimal point, trailing zeros are not significant. The trailing zeros are the ones that change depending on whether or not there is a decimal point. So in all numbers, zeros which appear between non-zero digits are always significant, and leading zeros are never significant, though you really only see leading zeros in numbers with a decimal point. It's theoretically possible to write 0075, but no one would do that. So for example, 3400 has two significant figures. There's no decimal point, so those trailing zeros don't count. So this has two significant figures. Here we have 0.00010. I think I said the right number of zeros. The leading zeros are never significant. You can always ignore them. But this has a decimal point, so that trailing zero is significant. So the last two figure digits are significant. This has two significant figures. Here we have 0.000106. Again, leading zeros are never significant. Zeros in between other numbers are always significant, and non-zero digits are always significant. So this has three significant figures. And here we have 2050. The zero between other non-zero digits is significant. However, the trailing zero is not significant because there is no decimal point. So that's not significant. Those three are significant. This has three significant figures. And here we have something written in scientific notation. This is actually the number of particles in a mole. If you want something we just mentioned from the units, a mole is this number of particles. 6.02 times 10 to the 23rd. This is in scientific notation. In scientific notation, the zeros between non-zero numbers are going to be significant, and there is a decimal point. If you wrote it out like this, the trailing zeros would have no decimal point. You'd leave them out. This has three significant figures. In scientific notation, all the numbers shown in scientific notation are significant. The power of 10 is not. And that will always be the case with scientific notation. One of the nice aspects of it. So let's go through and rewrite these numbers using scientific notation, using the correct number of significant figures. So 0.0257. Anyone? This 0.0257. What would that be in scientific notation with the right number of significant figures? be to the negative 2. So numbers that are small have negative powers. Numbers that are big have positive powers. So 125.6, what would that be in scientific notation with the right number of significant figures? No, because you always want to have your decimal point immediately after the first digit. Positive 2. Yes, this is a larger number. So when you move the decimal point to the left, you add. When you move it to the right, you subtract. So this is 1.256. And in general, if it's bigger than 1, it'll have a positive exponent. If it's smaller than 1, it'll have a negative exponent. So big numbers are positive, little numbers are negative. 93 million. What would that be in scientific notation? That is correct. 9.3 times 10 to the 7th. Here we have negative 65,800.0. What would that be in scientific notation with the correct number of significant figures? That is almost correct. You got it correctly in scientific notation, you just didn't have enough significant figures. Because the decimal point is here, you have to include all these zeros because they're significant. So you get negative 6.58000 times 10 to the 4th. And then lastly, we have 0.0000278. What would that be in scientific notation with the proper number of significant figures? There are 5 zeros before the 2, after the decimal point. So between the decimal point and the 2, there are 5 zeros. That is correct. 2.78 times 10 to the negative 6. And I may not have mentioned this in this class, but for scientific notation, if you want to write an answer in scientific notation into the WebAssign homework software, this does come up in the getting started, the way you'd write it. Like, for example, this number, you write 2.78, and then instead of times 10 to the minus 6, you just write a lowercase e and then minus 6. That is the formatting that the online homework uses for scientific notation. A lot of your calculators will have like an E button. It'll say EE or EXP or times 10 to the power. Depends. That'll let you type in a similar way. Sometimes it'll use a capital E instead of a lowercase e, but that is the format that the WebAssign homework uses. Just wanted to go over that because people get confused about it every year. And it's just, that's how you type in answers in scientific notation. And there is an example of doing that in the getting started, but it isn't the most clear. And here is going the other way. We have numbers in scientific notation. We'd like to write them in standard notation. So 2.57 times 10 to the 2, how would we write that? So to undo scientific notation, you want to get the power to 0. You move the decimal point. So for example, here you'd move the decimal point to the right 2 places to get rid of the 2 powers of 0 because you want to subtract 2. So if you move this to the right 2 places, 1, 2, you will get 257. Then we have 1.25 times 10 to the minus 7. How many zeros did you have after your decimal point? That's correct. So it is 0.000000125. Because this time you have to move the decimal point 7 places to the left to get to 10 to the 0. Then we have 9.3 times 10 to the minus 4. That is correct. 0.00093. Then we have 6.580000 times 10 to the 4. What would that be? If I think you missed a 0 in there. It's 65800.00 because you move 4 places. And then we have 2.78 times 10 to the minus 1. What would that be in standard notation? Yeah, it's 0.278. So let's go through this list and place them in order of which has going from the most significant figures to the least significant figures. So which of these do you think has the most significant figures? This one is followed by 7 zeros after the decimal point, if you're having trouble seeing that. So you're saying, which one do you think is, you're saying this has the most significant figures? Or this? So that is correct, that has 8. So what's next? Yeah, the 890,000 has 7. 890,000.0 has 7. Wait. Sorry, I couldn't hear you. The 60,001, that is also correct. That has 5. What's next? The 1 million, this one. 1,501,000 has 4 significant figures. These are significant. The trailing zeros are not. What? Yeah, the 4,520 has 3 significant figures. And then the last one left is 0.00030, which has 2 significant figures. So again, overview of the rules. With leading zeros, never significant. Trailing zeros are significant if there is a decimal point. Zeros between non-zero digits are always significant. Numbers without a decimal point, trailing zeros are not significant. So 3,400,100 has no decimal point. So the trailing zeros are not significant. So this has 5 significant figures. Now, when you're doing calculations, these are the formal rules for calculation. For addition and subtraction, the standard methodology is that you use the answer that contains only the fewest number of places after the decimal point. I will not penalize you if you use significant figures for this. I'll accept that, but the standard rule is to use places after the decimal point. Usually significant figures and places after the decimal point give you the same answer. But for multiplication and division, you need to do the answer that contains the fewest number of significant figures. In general, I will just accept if you round to the fewest number of significant figures of your inputs, you get an answer. But the fact that it's fewest number of places after the decimal point is part of why you can get more precision, more significant figures out of doing things like averaging a whole bunch of measurements. Because this can actually increase your number of significant figures. So for example, 1.455 plus 3.2, that should be, strictly speaking, rounded to one decimal place, 4.7. But you'll notice, if you just did significant figures, you get the same answer. That is also two significant figures. So most of the time, decimal places and significant figures for adding and subtracting will give you the same thing. So it's fine. It's multiplication and division that significant figures are the more important value. So I won't penalize you if you use significant figures for adding and subtracting, but that is, strictly speaking, the right answer. Here we have 1.40 plus 0.21. This, two decimal places, this should be expressed precisely as 1.61. This would be two significant figures. So if you wrote 1.6, I wouldn't mark you wrong on a test or a quiz. But this is the, strictly speaking, correct way to do it. Here for multiplication, 1.40 times 0.21, that will come out to 2.94 and 0.294. However, 2.1 only has, like 0.21 only has two significant figures. So this needs to be rounded to 0.29. And here, 0.023 times 1,000 divided by 1.56 times 10 to the fifth. This we need to round to one significant figure because of the 1,000 only has one. So while this whole thing comes out to 0.038589743, we would round this to one significant figure because our 1,000 value only has one significant figure. We would round this to 0.04. And then here, we have 6.0023 minus 1.001 divided by 23.002. Strictly speaking, what you should do is do the addition. That should have three decimal places. Do the subtraction. That'll have three decimal places. And then you can do significant figures for the division. So the three decimal places in top give you four significant figures because it's 5.022. And then you have five significant figures in the denominator. So the answer should be rounded to four significant figures. But you'll notice if we just look at our inputs, this has four significant figures, this has four, and this has five. And we just rounded to four significant figures. So strictly speaking, again, you should do the addition and subtraction first, then do the multiplication and division rounding. But you're safe if you just take your inputs and look at what you get out at the end for significant figures, especially for more complicated formulas. So that was how you approach that kind of problem. Then let's talk about problem solving. So you're gonna have a number of problems that you're gonna need to solve. This is a sort of general technique you can use to work on solving problems. So the first and most important step is read the problem. Reading the problem is very important. It's important that you read what you're actually being asked for and don't answer the wrong question. People do that all the time. So when you have a problem, read the problem, try and identify the principle that is being talked about. Then, two important techniques: write down what you know from the problem. Go through the problem, identify what you know. Write down what you know, then also with units, and you can also make a sketch. Drawing a picture is often very helpful in figuring out what you need to know, what technique you need to use to solve the problem. Then figure out what's being asked for and write it down. So writing down what you know and what you're looking for is a great way to figure out what equations you'll need. Because the equation you'll need will have what you know in it and what you're looking for. If you can find an equation that has what you know and what you're looking for in it and nothing else, well, that's the equation you need. Then check your units. You may need to make conversions to the base units the equations run in. So, for example, lots of equations run in meters, seconds, and kilograms. But if you have a speed in, say, kilometers per hour, you'll have to convert that to meters per second to use in your equations. Then look over your equations and choose the appropriate one. You get a sheet of notes on all your tests and quizzes. So that's where you can write down all the equations you'll need. And then lastly, do the math using the appropriate units. And then finally round off and adjust to the right number of significant figures. Look at your inputs, find the one with the least number of significant figures, round to that. So here's an example problem. The Earth goes around the sun in a nearly circular orbit with a radius of 93 million miles. So how many miles does the Earth travel in making one revolution around the sun? So let's go through this and identify the important aspects. So the Earth is going around the sun. It's in a circular orbit. Okay, we're dealing with circles. Maybe I should draw a picture of this. We have the sun. We have a circle around the sun with the Earth, and it's going that way. We know the radius of this circle. Here's the radius. This is 93 times 10 to the 6th miles. That's 93 million miles. And the question is, how many miles does the Earth travel making one revolution around the sun? So let's think about it. What distance does the Earth travel going around, making one revolution around the sun? Well, it goes around the circle once. So that distance is going to be the circumference. So what we know things we know, our radius is 93 times 10 to the 6th, well, 9 point, I'll write it side different notation, 9.3 times 10 to the 7 miles. We are looking for circumference. We're dealing with circles, so also pi is 3.14159, So that's sort of a start to attacking the problem. So there's our picture with a radius, and then we're traveling around the circle. So we're dealing with circumference. What's the formula for the circumference of a circle? That's an equation we need to find. Well, we know the radius, we know circumference, we know pi because we're dealing with circles. So our equation, circumference, this should be a lowercase. equals 2 pi times the radius. So we want to calculate our circumference. We'll have 2 times 3.14159 times 9.3 times 10 to the 7 miles. Also, our answer needs to be in miles because we're asked for an answer in miles. Our radius is in miles, our answer is in miles. We don't need to do any unit conversions. So that saves us some trouble. So if we do that calculation, circumference is 2 pi times the radius. We get 3. For pi, we're using 3.14159. That is the 6 significant figure approximation for pi is a generally good solid approximation you can use almost all the time. I mean, yes, we know pi to like millions of digits, but in practice, you only need like 6. So that's 2 times 3.14159 times 93 million miles, or 2 times 3.14159 times 9.3 times 10 to the 7. When multiplying things in scientific notation, you multiply all the numbers in front of the powers together, and then when you multiply together the powers of 10, you add the exponents. There aren't any other exponents there. So this comes out to 58.433574 times 10 to the 7. You could write, then you have to round this off to 2 significant figures. You could write 58 times 10 to the 7 miles. That would be correct. If I didn't specify the answer needs to be in scientific notation, that would be fine. You could also write 58,000,000 miles if you wanted to. That's the same number. But the preferred notation would be 5.8 times 10 to the 7. You move the decimal place 1 point to the left. I'm sorry, 5.8 times 10 to the 8, because you move the decimal place 1 point to the left to get it in scientific notation. Any questions about that process? Again, writing down what you know and what you're looking for is a great way to figure out what equation. So, lastly, the equation that will show up, the one equation for this chapter, is that density is mass over volume. There's density questions on the homework. There'll be a density question on the quiz. Our next lab will be about density. Density is written with rho. For solving problems, you can also use a capital D. I won't mind. But the textbook uses rho, which is a Greek letter. And it's mass divided by volume. You want the other versions of this equation where you rearrange these 3 equations of the same equation, just rearranged to solve for different values. Mass is density times volume. Volume is mass over density. That covers all possible things you're trying to solve. So are there any questions about chapter 1? Okay. A reminder, your first quiz will be Monday in the SI session at noon, which will be in room 332. I'm gonna stop sharing and end the meeting.